this one work? Oh, that one. Okay. Good. So, there were a couple of good things about the chat we have on Slack. One is that some people, said, oh, it really helps me that I know rock a little bit to understand what we're doing. So that, finalized my decision to do rock today and then universes when we get to that pain point in rock. But there were 3 really good questions yesterday that I think it's quite good that we visit or revisit them today, so for everybody. So I want to do that first, and then, I promise you some coding. Okay, so first question was, how can we, so maybe I can write it down. How can we construct elements in the propositional equality type that is not REFL, right? So non-REFL elements of the equality type. Okay? So we actually already constructed some yesterday. I just didn't pinpoint it to you. So we had yesterday the inverse function, right? So for A being a type, if I have X and Y of type A, then if X equals Y, then Y equals X, right? You remember that? And we defined it to be inverse colon equal, and then it was J lambda X REFL X, something like this. Now, actually, if you see type here, this codomain, it's the identity type, right? It's a propositional equality. So suppose I can use this function inverse on, I don't know, for natural numbers, and then I have 0, and then 0, and then I give it a proof of 0 equals 0, which is REFL 0. This will be of type 0 equals 0 at natural numbers, okay? Now we know that REFL 0 is of type 0 equals 0 at natural numbers, but now I have an entirely different one, syntactically different thing that is also in the equality type, right? And I can unfold this and I can say actually J at lambda X, REFL X at 0, this is the function application, right? Is also of type 0 equals 0. At natural numbers, right? So I have a term that is actually J applied to stuff, right? And it lives in this type, so it's not just REFL, it's also this one, okay? I can give you an even like simpler example. So suppose we want to construct a term of type pi x in natural numbers, x equals x in natural numbers, right? Now, the simplest way to do it would be lambda x, REFL x. Okay, again, REFL is the simpler one. But I can also decide to do it, okay, let's do it with induction on natural numbers, right? So it's not going to be just J, I can just say, okay, it's induction on natural numbers. And then I have to give it the, the type family, we know. And then it's going to be, okay, so what will be the type family? So the type family will be actually this, right? Because if I want to do, so this is P of x in our induction principle for natural numbers. And then I have to give it for 0, which will be REFL 0. And then I have to give it a successor, which will take lambda n, and then lambda little p, which is the proof that n equals n at natural numbers, right? And now I have to give it a proof of successor, and I could just say REFL at, so I have 2 options here, but I can also just complicate stuff and say, okay, I'll do the action on paths, so I'll get AP suck, and this one, if I apply this one to this, will give me suck n equals suck n at natural numbers, right? So I can just say absuck, how many arguments does it take? So I have to give it 2 arguments, n, and then p. So this p here is this p, and this p is a proof of n equals n. And this guy, this whole term that is induction on natural numbers is also of type 0 equals 0 at natural numbers. So indeed, it's not just REFL. We can construct stuff, and how do I construct this stuff? Well, I use the eliminators of the other types, right? Because the eliminators tell you how to get out of the type, how to create functions out of the type, but the codomain of this function can be the identity type, right? And then I can basically construct stuff in the identity type by using the eliminators for, other types or even the same type. Yes?
Intuitively, I would think that that's a proof that every every natural number is equal to itself, but you're saying it's of type 0 equals 0?
Maybe I have to apply this to 0 too.
Oh.
This is here the function application. Thank you. Very good. So, I have now 4 different terms of type 0 equals 0. So not everything is just REFL. Yes, question?
Are any of them convertible or judgmentally equal to REFL?
Probably. Yes. So this one for sure, right? Because we know that there is a computation rule on natural numbers, right? And it will just give me REFL 0. So they are judgmentally equal in this case, yes. But we could have, so if I don't apply it to the natural numbers, if I just take this thing, right, and then I give it a variable, x, okay, I put x in the context, then I can have REFL x, and I have this thing applied to x, and that will not reduce, right? So it really is fundamentally not necessarily judgmentally equal term. Yes. Okay, so this is question number 1. Then question number 2 was what would be an example when we have the J rule, right? We have, okay, let me just write the first, right, so we had context gamma, then x in A, y in A, p in x equals y in A, and then we have big P of x, y, little p, and this is a dependent type, right? It's a type family. And then the question was, how do we construct a type family that depends on this little p actually, right? Because so far, we kind of always had, just a type that doesn't really depend on the p. So I have a somewhat artificial example here. I think it's artificial because we just don't have enough theory and enough proof development to give you something more reasonable and concrete. But for example, I could form a type. I could form a type that says I have x in A, y in A, p that is of type equality between x and y at A, and then I can have something like okay, sorry, all of these a's are natural numbers. So I can apply the successor function absuck to x, y, p, and I say this is equal to itself. And this happens at type that is suck x equals suck y. Okay? So the type of this equality, right, which happens is also an equality. So it's like one level up. And now this entire term.
Can we write larger?
Yes, but I think this will probably be one of the last things I will write. So, do you want me to rewrite this whole thing? I can. Okay. X in natural numbers, y in natural numbers p x equals y at natural numbers, and then I have app. This is the action on paths with the index suc. This is the function of x, y, p, and then equal the same thing. App suc x, y, p, and the type at which this equality happens is suc x equals suc y. Okay? So we're equating it to itself. So of course we can just say the term will be called raffle, right? But the point is that the type specification itself, the type family, explicitly mentions p. Okay? So it's an action dependency, and of course the role of p here will not be to, inspect its, to pattern match on it or whatever. So if we pattern match on it, we'll just have the raffle case and so on and so forth. But the point is that sometimes you want p to be there, right? You want to have a reason to believe that x and y are equal. And you do this by having an explicit dependency on p, saying, I cannot form this term without knowing that x and y are equal. And then suc n and suc y are equal. So indeed, we can have a proper dependency. Of course, it helps that this is also the equality type, right? And then forming new equalities requires to have proven previous equalities. So this is where this dependency comes from. But when you look at this here, I cannot just remove p from the type family, right? It's an actual dependency. Question?
Weird question, but I interpret REFL x to the term REFL x to be a proof that x equals x. I'm a little confused by the idea of REFL x equals x. Is that a proof that x equals x equals x equals x? Like, I don't know exactly how do you interpret the equality of things of type x equals something?
Yes, so you interpret them exactly like this, right? If I have a equals b, and I have a proof that a equals b, then I'm saying, okay, this is one proof that a equals b. But then I can have two proofs that a equals b, okay, and then I can have a type saying p equals q, that the proofs are equal, so it's of the type of this propositional equality is another propositional equality. So this is, like another level. I'm saying that two paths in the identity type, two proofs of this equality are also equal. Yes. Nothing is stopping me from doing this, so I can. Okay. Did I convince you that you can make a proper dependency? Who is convinced? Hands up. About the third. Okay, question?
Yeah, just the reason that the right-handmost propositional equality is of type suc x equals suc y is because we're using the action on paths on.
Yes.
Yeah.
Yes, exactly. So this term here, right, is of type suc x equals suc y. Because the action on paths will take a proof of x equals y, and then we'll just stuck suc on both sides. Yes. Okay. The third question I got yesterday was about heterogeneous equality. And this is a fun one. So maybe I can give you a hand-wavy example on the whiteboard with a half promise that I will code it up in rock, and then if I don't really manage to today, you will for sure get it in the notes. I will, I'll give you the code later. I just don't want to spoil the fun. So the very good question that I got yesterday was, okay, suppose I have the vector type, okay? I have vec an, right? And then I want to concatenate two vectors, right? So I have the concatenation operation, like v plus u, right? you can, I'm sure you understand what concatenational vector is. And then I also have the reverse operation that will just reverse all of the order of all of the elements, right? So this one will have type like a m, like a n, like a m plus n, and this one will just have the same dimension, so it doesn't change the type, right? Okay, so here, you know, u and v are abstracted, so I should say lambda v, lambda u, v plus this u, okay. Now, what you would want to do is combine these two, right? So I want to say, if I concatenate two vectors, and then I revert the result, it's the same as if I reverted one, reverted the other, and then concatenated them in the wrong, like the opposite direction, right? So I want to say that reverse u plus v is equal to reverse u, no, first reverse v, and then plus reverse u. Okay? Now, I'm pretty sure we all agree this is what we want to be able to say, but the problem is we cannot really say that, okay? And this is because the types don't really match. Like u plus v is of type vec m plus n, well, a, sorry. I will write this larger. Here we have vec a m plus n for this concatenation, and then reverse just keeps the type. Whereas here I have vec n and then vec m, so we'll get vec a n plus m. Okay? So the types don't match because m plus n is not judgmentally equal to n plus m, right? Unless the second argument is 0, right? But in general, it's not. So actually, I really cannot even write this, okay? So this here is not derivable, even as a type, right? I'm not even talking about the proof, right? The proof here, right, is not even mentioned yet. I can't even use the type formation rule for this. So what we have to do is, we have to here, I'll use a color that you can actually read. Here, you have to insert the transport, okay? And the transport family, right, will be lambda d vec a d, right? So the dimension of the vector has to be abstracted away, and then you have to prove the equality that m plus n equals n plus m, and then insert it into this transport to actually even form the type. Okay? So hopefully I will show you that ROC just won't have this. Right? It will complain. You can't even state the equality, but if you insert the transport, which is slightly painful, then you can state this. And the reason to have heterogeneous equality is because you want to be able to say this without manually fiddling and saying what the transport is. Because, obviously we want to say this is equal without worrying that, the types are, kind of equal. Okay. So that being said...
I think there's a question here.
Yes, where's the question?
Over here.
Yeah.
One last question about the members of REFL X. It seems that there can't be, like...
What do you mean members of REFL X? Members of propositional equality?
Oh, sorry, I meant, yeah, the members of X equals X, or some X. What is wrong with, like, thinking that all the members of X equals X are equal to each other? Is it just wrong and it'll give you, make you prove many bad things? Or is it true but we can't prove it?
So this is a special axiom that you can add. It's called the uniqueness of identity proofs. Okay? And it's consistent, but it's not necessary.
Okay.
Yeah. But it's, you're not the first one to ask this question. It's a really good question. Yes. So the uniqueness of the identity proofs says exactly that. Like any two proofs of equality are equal to each other, and that's okay. It's a consistent thing to add to Martin type theory. Okay. Can somebody tell me how to drop the thing so I can project my screen? Yes. I have to press something. Ceiling. Okay. Thank you. Thank you. All right. So hopefully I haven't checked, but Jim can confirm that these slides should be available already on the webpage. Yes, they are. Okay, good. There are not many slides. I will mostly just be coding, but because some of you, and there is very few of you who haven't actually done any rock so far, there are like just a few introductory slides, and then towards the end I try to include some stuff about how calculus of inductive constructions is different from Martin type theory, and this is more connected to the universes thing that we haven't done yet. But just to get you started, I will give you a little hint of how to use this thing. All right. So now I'll need both hands, but I have. Is this still okay? You can hear me? Yeah, good. So, first, Valeria shared her groupie photo, and I want to show you my groupie photo. So here is, I'm wearing red, so this is me. And this guy is Martin Love, and the woman next to him is Paige, so this is also her groupie photo. So yeah, this was in Stockholm in 2022, I think. So I really, this is my proof, not AI generated, that I actually saw him and interacted with him. All right. Official rock documentation is available on the internet. This is an important disclaimer. This lecture will not cover the full power of rock, just the basics, and the point of this whole demonstration is to show you how you interact with the rules of the type theory and how they show up in rock. So if you haven't done any proof assistant so far, this might be a bit weird place to start. So if you don't understand what I'm doing, just say it. Also, I haven't really used rock in quite a long time. And there are people here who have done, only rock for the past 6 months or more. And if this is you and you see me struggling with the syntax because I have done 3 other syntaxes in the past year, please just, help me out. I'm not pretending that I'm a rock expert. I'm not, but I'm, kind of a type theories expert. Okay. For the beginners, rock files are text files ending with .v. And you can type check a rock file from the command line with rock C here or rock compile. But the preferred and the usual way is to use rock top, and this is integrated with either the rock IDE or your favorite editor. I will use VS Code, not very proficiently, but good enough. And the comments are written in 2 stars like this. So if I have something like this, and you can't probably see well enough. So, is this big enough? Yes? Good. Okay. So I can say this is a comment, and it's all fine. Just give me a sec. I have a cheat sheet of what I wanted to say today. open it up. Okay. So what we can do, oh, I have another slide. Coq commands end with a dot, and this is the syntax for the definitions, right? So everything you want to derive, kind of, any lemma, any theorem, any definition you want to make, you have to give it a name. So the usual syntax is definition, and then you give it a name, and then type, and then you define a term. And we will do function types first, because that's the most natural one. So of course, I will define you the identity. So the first derivation we did was the identity function, so let's derive identity here. So I say definition, and then I have to give it a name. It will be, of course, called ID1, because ID is already taken. And then I can give it, I can say A is the type, okay? And then the type of the identity is from A to A. Okay, and then I will just define it what I want it to be, and I'll say colon equals fun x, and then equals arrow x dot. Okay, so this means this is the syntax for lambda, so this is lambda x x. Okay, and if I wanna check that what it is, so in VS Code that I'm using, I will just call this command prompt, and I'll write coq, and then it suggests a few things to me, and they already have some shortcuts. So one is interpret to point, so it will just interpret to where my cursor is, and I will use the one that's step forward, right? So if I step forward, something gets colored green, and it says here on the side that ID1 is defined, okay? So congratulations, you defined your first symbol in Rock. It's the identity function. Okay, we can check what this animal is by using check. So check ID1 will print the type of ID1. So here on the right hand side I have ID1 is of type for all A type, A arrow A. Now this colon here, usually I didn't write any colons when I was writing on the board. And this is because Rock actually pretends that this A belongs to a universe called type, right? And these are the universes that I haven't told you yet about. So for now, if you don't know what they are, just pretend that this colon doesn't exist. Pretend that this is just Coq syntax, Rock syntax for saying that A is a type. Okay, so I can also print ID1, and that will give you the full information it has, including which concrete term it is. So I gave a concrete term here. So you can, basically just say, I have something of type this, and then I give you the term, and we didn't even write the derivation, right? Because the derivation tree is what Rock does for you, right? It's just computed away in its type checking algorithm. And because it does all of these things automatically, we'll sort of pick where we can see where the rules are being used. Okay, now this is not really standard way to prove stuff in Rock. Well, once we're done with our definition, we step through it, and then it colors it green so that you know what's been checked so far and what not. We have check T and print T, and usually we don't really write the full explicit terms. Usually how we